Hi there, so I'm Kit and welcome back to Gorilla Physics, a show where we really care about your student success. So Silas agreed to bring his guitar in today to give us a good context for understanding how standing waves on strings work. Okay, so he's going to take you through frequencies and wavelengths, how they're related by the wave speed equation. So thank you very much.
Gorilla Physics.
Yeah. If you want, you can have a shot of Gary on the guitar if you really want.
Yeah, that would be awesome. Rock on, Gary. He's left-handed, isn't he?
Yeah. Hello, I'm Silas and I'm in year 12, and my wonderful physics teacher, Mr. Gorilla himself, the other day showed me it was a virtual keyboard, and he showed me that if you go up an interval of an octave, which is basically, it's the same note, just up in pitch. So I'll show you. So if I play an open string here, can you hear that? Now if I play it up an octave, it sounds like this. So you can hear how they are the same note, just up in pitch. Now this doubles the frequency of the wave. Now the way this works is that you use the equation wave speed equals frequency times wavelength. And if I play a note, if you think of the wavelength, or half the wavelength even, being from here to here, so it's like so here's the crest, so you can see that kind of wave. Then if I play up the octave, then it's only this part of the string that's now moving. So the wavelength has been reduced by half, because this spot here, where I play the note to go up the octave, that is exactly halfway between here and here. So if we half the length of the wave, because wave speed is the same, we have to double the frequency, which is why it sounds up an octave. So we can do this again by halving this bit of the string again to get the next octave, which is about, I don't know if you can hear that, but you can hear that's similar to, that's up another octave because we've halved the string again. And if we wanted to find the next octave up, we could half it again. So here we have a ruler, so we can see that the exact distance from this bridge to this bridge is 65 centimeters long. And we also see that up to here, where our octave is, that is 32.5 centimeters long. So that is exactly halving the original wavelength. So we can go up half 32.5 to get 16 and a quarter. So you can hear that's where the next octave is. And then we could do half of that again to get about 8. And you can just about hear that sounds the same. Now I talked about octaves, and this also works if we start on a different note. So if we go like this as a G, you can see I'm pushing my finger down here, and so the wavelength is from here to here. Now if I then play up an octave, so at half the string size, that's where I put it, because then that is still then half of here, the distance from here to here. So you can hear that, how that's half. So Gary wanted me to prove this. So I loaded up a program called Audacity, which is great for working with sound waves. And I wanted to visually see how the wavelength halves. So I played one note into it, and then got a wavelength. And then I played the octave above, and I recorded both, and then I put them by each other. And you can see that the wavelength is halved, so therefore the frequency is doubled. And now I'm going to talk to you about harmonics, which is a certain technique where instead of placing your finger down fully, you lightly leave it over the string. So then you still play it. So you get that higher pitch sound instead of the usual low one you should get. Now this is because by leaving your finger here, this bit is not the wavelength anymore. It is just this bit here. Because instead of pushing my finger down, because I'm lifting it there, that is because my finger is basically acting as the midpoint of the wave. So when it goes up and halfway in between a peak and a trough. So then this is the wavelength here. So then also, if that is, no, sorry, that's half the wavelength. If that is half the wavelength then the next half of it will come to about here, because it will go like that. Now, if we rest my finger here, we can hear the same note again, because it's the same wave, just divided up, and this is the same for other places as well. So you can hear that? See, that is the same length again. So when I was saying about the harmonics, when I was saying that when you lightly rest your finger to produce a harmonic, you put your finger on specific nodes, which are these bits here, the middle bits, the nodes, and think of this line as the string, and these bits as the nodes, and each place you can put your finger along here, and it will produce the same sound because they're the same wavelength. And one other thing is that when I play the octave, the first octave, there is also a harmonic you can do there as well. However, you'll hear that that is the same note, because when we play the normal note, that's reducing the wavelength to half the wavelength, sorry, to be that. However, when we play the harmonic, it's divided up into two. So it is essentially the same wavelength, just one full wave rather than just half of it.
It's absolutely amazing, thank you. And I think it's absolutely fascinating, isn't it, how just certain frequencies, for some reason, as humans, sound good to us. So
All harmony is based off just the length of the waves that they produce. It's very interesting.